This problem is going to repeat itself in all the algorithms that I'm going to show you. Here's another algorithm. It's called fitted queue iteration. It's also very old, FQI for short. And it's a very similar idea. Here we say we want to create a training set to train on. Okay, we want to create a regression problem for the queue function. So again, recall that we have tuples of state, actions, rewards, and next states. That's our data set. And now we need to create our labels to solve the regression problem. So our labels are going to be the what we saw in the Bellman operator, Ri plus gamma max of Q. Now, if we didn't have this max here, then I remind you that this is actually another way to write the Q function, right? If we didn't have this max here. What this max here does is similar to the greedy policy that we saw here. It takes the greedy Q function. Okay? So these are our labels. They're trying to improve our policy. We're going to create a training set that its examples are going to be the states and actions. The labels are going to be, the targets are going to be these yi's, the Ri gamma max of the current Q. And we're going to train this using some regression algorithm. It could be a neural network, random forest, whatever you want, some kind of regression algorithm to learn a new Q function. And then we'll repeat this process. Again, we would make new targets. That would be the Ri plus gamma, the new Q. And again, train on the data set, so on and so forth until we converge. What's the problem here? This is a very inefficient process. And again, we have the action distribution shift problem that I told you earlier. Regarding the inefficiency, we can actually make this algorithm pretty good. So in 2015, DeepMind came up with a pretty nice algorithm known as deep Q learning, DQN. And DQN, so it's kind of one of the first breakthroughs in deep reinforcement learning. The algorithm is basically FQI, the algorithm that we saw here, fitted queue iteration, only it changes it a little bit by adding an experience replay and a target queue network. Okay, so in the general case, we can assume we have a lot of different queue functions, a lot of different local queue networks that are going to interact with the environment, gather experience for us. Experience is tuples of states, action, rewards, and next states. So we're going to interact with the environment and receive these states and actions. We're going to execute actions, and we're going to keep these. And from all the different workers, we're going to save these in some experience replay. So this is a queue that is going to save all of the data of states, actions, rewards, and next states that we gathered while interacting with the environment. Recall that this is an online algorithm still, which we're gonna turn it into an offline algorithm. But in general, we have interactions with the environment, and we're putting all our data into an experience replay. Then this experience replay is going to be used to sample from, like a data set, and fit a queue function and a target queue function, which simply the target queue network simply updates slowly, using the Bellman loss that we saw, and update accordingly. Now, why is this algorithm important? Because in the offline case, we're going to remove these workers, and we're going to only have data. The data is only going to be the experience replay. We're going to do the same thing, only with an experience replay, which is the data that we gathered. What is this loss function here? This loss function is basically solving the regression problem, right? This is the squared loss, where our labels could be something even a little bit more complex. It's very similar to the Bellman update that we saw. Over here, it's a little bit more complicated with a multi-step return, but it's not important for the matter, okay? Okay, what are the problems that we still have here? Again, this algorithm is great. It can use offline data, but we still have the problem that we might have data that we can't see. We can't gather new experience from places that we don't know about anything. And also, we still have this distribution mismatch problem, right? We're trying to fit a queue function, but the policy that generated the data actually took actions using a different distribution. So we're fitting our queue function with something that was sampled differently than what we're sampling. And this is problematic. Actually, this causes overestimation of the Q values because we're taking the argmax every time and we're fitting to something that was sampled from a different distribution. This causes overestimation of the Q values, and this is very problematic. This can maybe give us on offline data pretty good performance, but it's not optimal. It's not the best thing that we can do. So what can we do? What are the challenges of offline reinforced learning? What can we do to actually solve these problems? And there are a lot of problems here, and most of them we're only starting to scratch the surface of what to do with them. But I'll give them here in general anyway. So one of them is generalization, right? We want to be able to say something about states that we don't see in the data. Okay, so this is a pretty important problem. It's even more important than what we're used to in supervised learning. If we have an infinite amount of data, then we don't really have a generalization problem, right? But in reinforcement learning, since the policy that took the data might only take us to certain states, then even if we have an infinite amount of data, we might not see certain states in the data. So it's even more important, even if we have an enormous amount of data, to be able to generalize here. This also acts with the problem of uncertainty estimation. How do we know where we don't know something, right? So for example, the Q function. How do we know where our estimate of the Q function is biased? Is there any way we can know this? How do we estimate uncertainty in the Q function? How do we estimate uncertainty in the current state or in the model of our transitions? Narrow distributions talk about the problem where a policy might only take us to specific states in the state space, and we might not be able to see many things. What do we do in these cases? Suboptimal examples are, of course, a very important example, because data is almost optimal. We're in a very good place, right? Because we can try to maybe improve it a little bit, but in general, we could imitate and clone what the data is doing and will be good. We have a lot of suboptimal examples, a lot of that kind of data, then imitating this kind of data is not the best thing that we want to do. We want to really improve upon this data. Partial observability is a very important problem. I will not talk about this, but it's actually a very difficult problem to deal with offline reinforcement learning rather than online. In online reinforcement learning, we actually know how to deal with partial observability. But in offline reinforcement learning, this becomes a very big problem, because the actual the agent that maybe took the action maybe did saw the states that we didn't see, and this causes a lot of biases. So this is something important to remember, that in offline reinforcement learning, this problem of partial observability becomes much more important than what people are used to. Continuous time is also a pretty big problem, because when we get data generated in real life, it's not necessarily fixed to certain timestamps, right? It could be something continuous. It could be something that is non-uniform. It might be much harder. Also, we have a problem of non-stationarity. If a human will generate our data, then nothing promises us that this human would be stationary. So this is also quite a big problem. Today, there are in general two methods or paradigms to try and solve offline RL problems. One approach says be proximal. Proximity-based methods, what they do is they try to solve the regular algorithm that you would solve in the online case, while always remaining close to the data, meaning always remaining similar to the distribution of the policy in the data. Okay, so they're trying to be pessimistic in a way that would be close to the data. Uncertainty-aware methods do something a little bit more general. They assume that we have some kind of bound of these out-of-distribution estimations. So we have some kind of bound of how certain we are in certain states. For example, maybe we have an uncertainty measure of our Q function. And if our uncertainty is high, we try to stay away from these areas. So we try to stay away from areas of high uncertainty and remain close to areas of low uncertainty, right? We want to be certain of what we're doing. So those are a type of methods that can be used for offline reinforcement learning. Remember, in offline reinforcement learning, the problem is that if we try to solve the RL problem normally, then we're actually optimizing on places where we're very uncertain, and we're optimizing on noise and action distribution shift that could cause us to get very large errors in our final results. So this is why proximity and or uncertainty are very important methods for offline reinforcement learning. Let's look at some examples of algorithms that use proximity and algorithms that use uncertainty. So these are pretty recent. All of the algorithms here are from the past 2 years. Batch constrained deep Q learning, BCQ, and you don't have to go through the whole algorithm here. The basic idea is very simple. The basic idea says we're going to build a model for the policy in the data. So a model for taking action A given we're in state S. Okay, so this is P data of A given S. And we're going to play according to this policy, and we're only going to allow perturbation around the policy in the data. So we're only going to allow, so this is a proximal method, right? It's only going to allow us to play a little bit differently than the policy from the data. And it's going to do the actor-critic type algorithm that I showed you earlier. We're going to fit the Q function. and then we're going to maximize the policy, but we're going to constrain it to this set of perturbations around this action, which was sampled from the actual behavior policy in the data. Okay, so this is one type of algorithm. The problem here, that if we have very suboptimal data, then we're actually staying similar to this suboptimal data, and this is not good. Maybe we want to be good. This would work well with data that is good, but if we have suboptimal data, this would work bad. So what can we do? One way to think of a different method is, instead of trying to match the distribution of our policy to the distribution of the policy in the data, we can only try to match the support of the actions of the distributions, right? So this would mean that we're not trying to actually behave like the policy in the data, but we're only optimizing our policy where we actually have examples of actions that we're taking by the policy. So this is a proximity method that is much easier in a sense. It helps us not constrain ourselves to the perhaps bad policy in the data. Here's another method which is a bit more general. Instead of constraining ourselves in a way that would constrain ourselves to the data, to be pessimistic in a different way. So the regular regression loss that we saw before, the squared arrow, is this thing that you see here on the right, the Q minus the Bellman of the Q. Okay, so this is basically the same regression that we saw before, right? This B hat is the R plus gamma Q of the next state. Okay, so this is the regular thing that we saw in Q-learning, DQN. But here, to the loss, we also add these conservative estimates where the expectation is given by according to the policy in the data, or a policy mu that we can choose. So this creates a conservative lower bound over the Q function. And when we optimize over this lower bound, it allows us to be more pessimistic and not get such overly optimistic Q functions when we train the Q function. So it's pessimistic in a different way, right? It remains close to the data in a different way. It just tells us that instead of optimizing this with samples from the data, also optimize it according to some other policy that you couldn't currently taking, and this would not find the optimal Q function, but it would optimize a lower bound over the Q function. So these were okay. So here one of the problems is that of course this lower bound might not necessarily be tight. Those were examples of proximity-based methods. What would an uncertainty-based method look like? So in an uncertainty-based method, you could perhaps construct a model P of the world. So think about that. You have a data of states, action, next states. So a model would be learning the probability of a next state given a state and an action. So you could solve that using maximum likelihood, for example. You would construct a model of the world. And now we assume that we have some kind of uncertainty oracle over the model. So we know we can bound the error between our model, P hat, this is our model, the simulator of the world, and the real environment. So this is something that is going to be pretty hard to get, yeah? But assume that we have this upper bound over our model, then we can construct a pessimistic MDP that would say the following. Okay, you don't have to read throughout this math. I'll just tell you what it says, that whenever our model is very uncertain, meaning when divergence is too high, then go to a halt state where I would give you a negative reward. Otherwise, get the same reward and follow the model. But if you have high uncertainty, then stop the process and get a negative reward, some kind of negative reward. This would make our agent not want to go to areas of the state space where the model is uncertain. Another way to do this is through another framework called model-based offline policy optimization, MOPO for short, and it does basically the same thing. It constructs the model, it assumes that we have an uncertainty oracle over the model, can bound the error in our model in some way, this U, and then we simply penalize our reward by subtracting lambda times error in our model. And this again will make sure that we stay far away from states that we have high uncertainty in our modeling. And actually we can theoretically show that when we solve this problem like that, like I showed you right now, if we have this U function that can bound the error, then what we're actually be optimizing is a lower bound over the value function. So this is pretty nice because we know that if we optimize what I just showed you, then we're sure that our value would be at least as large as this. How can we estimate this uncertainty, right? This U, I told you that we have some kind of upper bound of our model. How do we estimate this? So this is actually pretty hard, right? So the whole problem How do we measure out of distribution? So this is related to out of distribution detection. So we could use things like confidence set, UCB, LCB, if you know, ensemble methods, which use we have several models, and then we can look at their disagreement to get a measure of uncertainty. Monte Carlo dropout. We have things like we could use variation autoencoders or VAEs, right, or something like that to model the distribution over functions, and then we could use the actual distribution to gain a measure of uncertainty. And there are many more methods. You can even look at one of my papers called Gelato, which I give another uncertainty estimation protocol that you can use. Okay, so that's a little taste of offline RL and what we can and what algorithms and what methods we can use. The benchmarks that are currently available, there are two benchmarks: D4RL, mostly for continuous control tasks. They have different quality of data sets there. Where what's nice about these data sets is you actually get both the data set that was generated and also a simulator of the problem, so you can test your algorithm to see how good it would be in this real environment, right? Because we need to test to see how algorithm is good. RL Unplugged is also nice. It has a lot of data sets collected by algorithms actually on Atari games, and also continuous control tasks. And again, you have the simulator there with you. And I'm assuming there will soon be many more data sets and we'll be able to use. What about evaluation protocols in offline reinforcement learning? This is something that is currently not established. There are two general ways that we can think about evaluating an offline RL algorithm. We could go to the real environment, right? We can actually interact with the real environment to see how good our offline RL algorithm is. But there are two problems with this. First of all, this is not realistic, right? If we have an autonomous vehicle, then assume that every algorithm we can go and now test in the real world, right? We might have problems doing this. We can't do this constantly anyway. Also, it might be very biased. So if we're trying to create a very general algorithm, but we're going to fit it every time to the real world and search for hyperparameters in the real world, then maybe if the real world was different, or we might overfit to this scenario and get biased estimates of the actual algorithm, how this algorithm actually would act in the real world. Something else that we can do is try to validate or evaluate our algorithm on offline data, right? Instead of trying to do it in the real world, we can do it offline data. This is much more realistic because offline data is something that we already have. We don't have to go to the real world. It's much easier, but this comes with a lot of different problems. So first of all, unlike supervised learning, where we can actually take a training set, a validation set, and train on ground truth labels, here we don't have ground truth labels, right? We want to know how good our new policy is, but we have a different policy in our data. So we have to use things like off-policy evaluation, which will tell us how good we would do. The problem is that current approaches for off-policy evaluation don't scale well, and even if they did scale well, they're imperfect, right? They give us an estimate of our value. They don't give us a ground truth label of our value. So we have to deal with these estimates of values and this imperfect selection. Also, there's a problem of what data should we use, right? So we use the full data. Should the data that we're using involve different states to check for generalization? How do we evaluate our algorithm? How do we tune up hyperparameters? So there are a lot of interesting questions to ask here. How to evaluate our policies, and we're only starting to scratch the surface, as I said before. So thank you.